So here we are going to talk about the branch target address. And I briefly mentioned that in the previous slides. And we said that, so for example, here, we said that when you have this label and you are basically assembling that, this label somehow gets converted to this I value. And that is what we are going to look at here. So the branch target address is basically that calculation and is basically the formula of how that I value is calculated. So what we're doing, so first of all, there is two parts to this formula. So one part is that you have this BTA. So, and that's the target address that we want to be. So if you have, for example, let's say BGE something and then you have loop. And then this loop has some address, right? So that's some address that this one has. So BTA is actually the address of this loop. So that's exactly the branch. So if this branch is true, if this condition is true, we are jumping to loop. So this BTA is the address of loop. So that is basically the target address that we want to end up on. So that's like our destination. So BTA is equal to address of the branch. So that is basically the PC or program counter. So that means it's going to be the current line of the code. So if you are doing, let's say, 000 10001 08 and then C. So this is continuing and then like 1 0 and so on. So let's say I have this. So this is my lines of code. So each line of code is actually in the memory location. And let's say here I have this BGE and then here is the loop. So my instruction that I'm running, the branch is on this line or on this memory address, and the loop is at this memory address. So the branch target address is actually this one, this address here. So that's BTA. My address of branch instruction, or that's going to be program counter or the current line. So if this one is here, this BGE, so my branch instruction is here. So address of branch is going to be this address. So that is going to be where am I in the code right now? Because here the goal is to calculate the offset. You want to do a jump, but you are jumping relative to the current line of code. So you're not jumping like giving an absolute value here, even though you are giving a label. So I think maybe that's the most important thing to understand here, that you are giving a label, right? You're on your branch, you're doing BGE, some registers and a label. And then you have your labels number. So that sounds very absolute to me, right? So because you're jumping from anywhere, you're jumping to loop. So that's very clear. But how actually it works is actually this label is being replaced by a relative value. So it's gonna be telling the processor how much to jump from the current location. So that is basically the kind of like relative. So it says, so if I want to like simplify it, if I say I'm on line 1, 2, 3, 4, 5, and then my branch is here, BGE, and loop is on line 5, my final thing that I want to store in my instruction is basically telling to the processor to jump like 1, 2, 3 lines. So that's like what I want to say to my processor. So if I had this BGE same with the same loop, I would tell him to jump like 4 lines. So it's very relative to the current location. So that's why we are using this formula. So branch target address is address of the branch instruction. So that's the current line plus 4, and I'm going to tell why 4, and then plus offset. So this offset is basically the kind of the difference here, that how much I want to jump. Almost, not exactly, but almost. We get there. So let's talk about. So the BT is clear, PC is clear. PC is the current line, BT is the final location. So why 4? So 4 is actually, we have this 4 because always at the end of any instruction. So let's say this wasn't a branch instruction. So let me clear that. Let's say this was LI here and something, and then I have like an add, for example. So at the end of this line of code, I'm actually going to the next line, right? So always the processor is adding a 4 to go to the next line. So it's always going to the next line anyway. So that's a program counter, like it's pointing to this location, line 2. After this line is executed, it's going to add 4 to this program counter so it can move to the line 3. So this 4 is kind of there to basically count that we're gonna add 4 anyway to the program counter, whether we are jumping or not, right? So that's basically accounting for that, because we are always adding 4. So let's we have to add that. So our offset gonna be basically 4 less, kind of, in a way. And then we have the offset. So offset is going to be that like difference in bytes. So that's a formula. And so we talked about that. And there is one more thing that I want to tell you, that so in the I format, so we said like BGE, we have this, and then we have a label, and we said we have this table that like we have, I don't know, 5 or 6, and then 5, 5, and then here we have like 16 bits. So this 16 bits is kind of the offset, but it's not exactly the same. So we are storing the offset here, but we are storing it in basically kind of number of lines instead of bytes. So when you calculate this one, this is 1 line, right? This is 4. That's 1 byte. Sorry, 4 bytes. This is in bytes. So that's bytes. This is bytes. And this is 4 bytes also. So what is our offset gonna be? The format or the unit, actually. So the offset is going to be bytes also. So the unit for this offset is bytes. But is there any case that we are not jumping like 4 byte, like a multiply of 4, or an offset of 4? There is no case, because we are never jumping like middle of a line, right? We are never jumping. So if these are lines, so it's ending in 048C. We never jump at like 10001, 0003. We never jump at that location, because each instruction is exactly 4 bytes, always, in MIPS. So we never jump at this offset, right? We are always adding, so this offset always gonna be a basically, if it basically, we can divide that by 4, and we're not gonna have a reminder. So basically that's always a multiply of 4. So then why to store here as a byte when we can store as number of lines? Because in that way, we're gonna be saving a space. So instead of I know like each line is 4 bytes. So for example, if I want to line from 2 to 4, let's say I wanted to jump let's say 3 line. I want to jump three lines of the code. I want to move 3 lines forward. If I am storing that in byte, I know each line is 4 bytes, so I have to store 12 here. But why would I do that when I can just store 3? Because always I'm gonna basically be jumping exact 4 bytes for each line. So here we can save some space. So that's why this offset that you calculate, you have to actually basically divide it by 4 and then you save it here. And that division by 4, it's basically shifting by right. So let me clear this. So our formula is BTA, PC, that's current line of code, plus 4, plus offset. But what you actually have in that I value in your instruction is not offset. So we have offset and we have I. So if you are converting offset to I, you have to divide by 4. Also, you can say shift right by 2, because 2 to the power of 2 is 4. So 2 to the power of 2 is 4. If you are having an I and you want to get the offset, you have to multiply by 4. And that's equal to shift left by 2. Left by 2. So then you basically, so you have 2 formulas now. So one is that when you want to calculate I, you put all the things that you have. You put your BTA, you put your PC, and 4 is a constant. Then it's a simple equation. You move this other side, you calculate the offset. But then that offset, first you have to do basically shift right by 2 to get the I value, and then the I value is what you care about. And if you are doing the opposite way, you have an I value and you want to get offset from that, you shift left by 2. And basically that's how you can do that. So let's look at examples now.